This is SpaceTime, Series 23, Episode 35. Coming up on SpaceTime, a new look at the origins of Earth's water, a key pre-launch test for the Hubble's successor James Webb Space Telescope, and it was to be a spectacular celestial light show this month and next, but it looks like Comet Atlas is breaking up. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims that Earth's water was born with the planet and didn't arrive later through asteroid and comet impacts. Liquid water is essential for life as we know it, and of course planet Earth has heaps of both. But intense debate has continued in scientific circles about exactly where that water came from. When you think about it, observations that Earth's rich in water is actually a little bit strange. At least it is when you look at other terrestrial worlds in the inner solar system, all of which lack surface liquid water. The abundance of liquid water on the surface of Earth is also hard to explain based on the giant impact theory, and that's a key part of Earth's early evolution. Basically, the giant impact theory explains how the early proto-Earth collided with a Mars-sized planet called Theia about 4.5 billion years ago. The cataclysmic impact turned both bodies into a molten magma ocean. Eventually, it cooled and solidified, forming the Earth we know today. And a little bit of debris and ejecta in orbit around the Earth coalesced to form the Moon. The problem is a lot of scientists have calculated that such a catastrophic event should have vaporized any existing water, basically leaving the Earth dry. Now, what all this means is that researchers are left with only two likely options to explain the presence of water on Earth. Either the water arrived later through bombardment by water-rich ice-laden asteroids and comets, or, alternatively, significant quantities of water did survive the giant impact. One of the big problems with the asteroids and comets scenario is the type of water they have. See, most of it's the wrong type, at least it is in terms of its hydrogen to deuterium ratio. In other words, it's not the same sort of water as what we find here on Earth. A major challenge in investigating the origins of Earth's water is that the planet's lost all traces of its early formation history. It's an active planet with erosion and volcanic activity, plate tectonics, earthquakes, subduction, and what all that means is that all the rocks which helped form the planet originally have now changed, they've metamorphosized into something else. So a bunch of scientists decided to look beyond Earth to its sister planet Venus in order to investigate the origins of terrestrial water. Both worlds were formed in the same part of the solar system, most likely out of the same sorts of materials and under similar conditions. But while the Earth and Venus are considered twin sisters, their evolutionary histories have diverged dramatically. Venus has developed into an inhospitable hell, with a crushing 92-bar atmosphere, superheated by a runaway greenhouse effect, with surface temperatures of 470 degrees, hot enough to melt lead. It does rain on Venus, but the rain isn't water, but rather sulfuric acid. It even snows on the mountain peaks, but instead of frozen water, it's metallic snow. However, the authors of this study believe Venus's volcanic activity and outgassing are reduced compared to the Earth because it has no plate tectonics and instead features what the authors have described as a stagnant lid. Even better, such a convective mode implies very little recycling of volatile chemicals into the mantle. And this means the evolution of the atmosphere of Venus is much easier to understand and model over geological time. The authors say that all these aspects combine to make Venus the perfect place to study the primitive evolution of terrestrial planets. So, using numerical simulations of different types of asteroids containing various amounts of water, the authors discovered that water-rich asteroids colliding with Venus and releasing their water as vapor couldn't explain the composition of Venus's current atmosphere. And that means that asteroidal material that came to Venus and thus also hit the Earth after the giant impact theory must have been, well, dry, therefore preventing the replenishment of water on Earth. So, the findings mean that the water we see on Earth today must have been here since the planet's formation, surviving the giant impact. The findings imply that the ancient Earth, as well as Venus and Mars, likely all formed with a near full budget of water, and then slowly lost it over time. Because Mars is much smaller, it likely lost its liquid water as the atmosphere disappeared into space. As for Venus, well, the results shine a complementary light on recent work advocating that water oceans did once exist on the surface of that planet, but have since all boiled away. It also helps to constrain the maximum amount of water that could be expected to be found on Venus, thereby providing important information for future missions to our sister planet. And you can read that study in full in the journal Nature Geoscience. This is SpaceTime. Still to come, the Parkes Radio Telescope undergoing a major upgrade, and a key pre-launch test for the James Webb Space Telescope. All that and much more still to come on SpaceTime. The CSIRO's iconic Parkes Radio Telescope is getting a major upgrade. The 64-metre dish is being equipped with a new receiver that will significantly increase the amount of sky it can see at any one time, thereby enabling new science. The project will see the development and construction of a new generation sensitive receiver called a cryopath. Once complete, the new cryopath will sit high above the famous Parkes Radio Telescope dish, receiving radio signals reflected up from the parabolic dish's surface. Its detectors will then convert the radio signals into electrical ones, which can then be combined in different ways so that the telescope can look in several different directions at once. In fact, the cryopath will have 3 times more field of view than the previous instrument, allowing quicker and more complete surveys of the sky. By the way, that name cryopath, well, the cryo means it's cryogenically cooled. That helps reduce the noise in its electrical circuits, enhancing its ability to detect weak radio signals from the distant cosmos, frequencies between 700 MHz and 1.9 GHz. And as for the path, well, that simply stands for phased array feed, a reference to the close-packed array of the radio detectors. The University of Western Australia will coordinate construction and commissioning of the cryopath, while the CSIRO will undertake the design, the construction and installation of the new instrument. And it's an area the CSIRO are well familiar with, as it's already designed and built phased array feeds for its Australian Square Kilometre Array Pathfinder or ASCAP telescope in Western Australia. And a test version of cryopath was already successfully used on the Parkes dish in 2016. And the technology isn't just confined to astronomy. It also has spin-offs in defence radar installations, in medical imaging, and even in optical laser beam steering, with emerging applications in satellite communications. The Parkes dish receiver is one of 2 major radio astronomy upgrades now being undertaken by the CSIRO. The other is for the Australia Telescope Compact Array near Narrabri. That will see the compact array's existing digital signal processor replaced with a new GPU-powered processor, effectively doubling the bandwidth of the radio telescope's signal electronics. The project, which is being led by the University of Western Sydney, will enable the telescope to study radio counterparts to gravitational wave sources and make more detailed follow-up observations of discoveries being made by other observatories such as the Square Kilometre Array. Professor Lister Stavelli-Smith from the University of Western Australia's node of the International Centre of Radio Astronomy and Research says the new Parkes receiver will help astronomers study fast radio bursts and pulsars and better map the universe through its hydrogen gas.
Well, they're both technology projects. On the Parkes telescope, the technology is what we call a receiver. A receiver is a thing which actually sits at the focus of the big telescope on top of the 3 supporting legs. And that actually is responsible for collecting the radio waves that we're trying to detect. Now, the technology that we're using, the phased array feed, actually allows us to detect signals from a wider area of sky, from a large number of pixels, almost 200 pixels, which doesn't sound very much from the point of view of, say, a modern CCD camera, but much greater than the 1 pixel, which many, if not most, radio telescopes have. So it allows us to take an image of a much wider area of sky and just speed up the amount of science we can do in a given time. The resolution is generally fixed by the size of the telescope. In this case, the diameter of the Parkes telescopes, that doesn't change. It's just the field of view.
So by increasing the pixels, you increase the field of view, the degree across the sky you can see.
That's right. So normally when we're doing observations with a telescope, we're making a map of an area. I mean, sometimes we're just looking at one object, in which case the field of view doesn't matter. But often Parkes is used in the survey mode. It's used for surveys of galaxies, surveys of pulsars, surveys of fast radio bursts, and in all those cases, the more sky we can observe at the same time, the more signs we get.
I noticed there's a smaller telescope located at Parkes as well. What does that little one do?
That is a little, variously used a test telescope, used to test bits of technology, but it can in fact be combined with the main telescope. And in that case, you do actually increase resolution because it then becomes an interferometer, and then the resolution is not just the diameter of the big dish, but is controlled by the separation of the big dish from the small dish, which is substantially better.
Can you increase that interferometer further by linking Parkes with the Australia Telescope compact array at Narrabri?
Yes, correct. In fact, CSIRO, which runs both telescopes, regularly links them up and other telescopes in an array called the Long Baseline Array, the LBA. And that array includes telescopes in Tasmania, run by the University of Tasmania, in South Australia, sometimes the NASA Deep Space Tracking Station outside Canberra, and also with the 22-metre telescope near Coonabarabran.
That's the MOPRA telescope?
That's the MOPRA telescope.
Yeah. Oh, that's good. I thought we were going to close that down. They haven't closed it down then.
Well, it's sort of run at a very low level and run with a lot of university money, particularly at UNSW. So it's not mothballed, but it's only used part of the time.
And of course, when we talk about radio interferometry, that leads us to the Square Kilometre Array project.
Yes, indeed, the Square Kilometre Array project, which is here in Western Australia. Correct, yes.
And there we have the Pathfinder and the MWA.
Correct. And there's quite a good link between the cryogenic PATH project at Parkes and the Australian ASCAP Pathfinder in Western Australia, because the Pathfinder, ASCAP as it's known, uses phased array feed technology as its front end. So not only is it an interferometer, but it's an interferometer of 36 individual antennas, each with one of these phased array feeds. So ASCAP has got enormous sensitivity and sky coverage and resolution, so it combines all of these attributes into one, what's turning out to be a fantastic array. The only disadvantage with ASCAP is that the phased array feeds are not cryogenic, and that's why, Parkes, we only need one cryogenic system to operate it, but with an array like ASCAP, we need 36 of them, which is a hugely expensive undertaking. But, at some point in the future, perhaps there might be some much cheaper cryogenic or cooling technology which can be applied. So Parkes is very much used to develop future instrumentation, and that will hopefully translate to other telescopes around the world and in Australia, and perhaps phase 2 of the Square Kilometre Array. And of course, being cryogenic has all the advantages too of specialised single pixel receivers. So it has incredible sensitivity, frequency coverage, and allows us to image a large area of sky. So to reduce the internal noise that's generated by the electronics, we like to cool things down as much as possible. And in this case, it's 20 Kelvin, 20 degrees above absolute zero. So it's pretty cold. And at that temperature, the sort of internal jiggling of the electrons is dramatically reduced, and that lowers the internal noise and stops it from swamping the cosmic signal that we're chasing.
To get a phased array down to such cold temperatures, what are you using as a coolant?
So they use helium.
Liquid helium.
Liquid helium has to be used to get down to those sorts of temperatures. And it's closed cycle, so there's a compressor which extracts the heat and cools the critical components down to about 20 Kelvin, but there's also less cool stages at about 100 Kelvin, which also benefit from the cooling, but the main thing is to cool the electronics.
Liquid helium's used all over the world for research. Unfortunately, it's becoming a little bit harder to get. Is there a helium shortage?
I'm not an expert on that, Stuart, but I gather it's becoming more expensive, but it's a finite resource. I think they get a lot of it from gas fields, don't they? And those have certainly got a finite lifetime.
Yeah, less party balloons in the future.
That's right.
The other major upgrade, of course, is for the Australia Compact Array. What's happening there?
So the Compact Array near Narrabri is also getting an upgrade. That is an upgrade of what we call the correlator. That upgrade is being built by CSIRO, of course, who own the telescope, and grant to to facilitate that upgrade is being led by Western Sydney University Professor Ray Norris. And that is really an upgrade to the brain of the telescope. It's a central signal processor which processes the data, the incoming electronic signals from all of the antennas, and basically combines that data to enable us to make images from the sky. Now, in the past, that's been done by dedicated pieces of hardware, but increasingly that's being done by off-the-shelf units, and in this case the proposal is to replace that central piece of electronics with quite a large number of so-called GPU processors. Those are programmable, but also very efficient and very power efficient, and much more so and much cheaper than normal CPU processors.
Most of our listeners would know what GPUs are because they're in their gaming computers.
Exactly, and the ones that we use professionally are very similar to the standard gaming units.
The end result of all these upgrades, what will that mean?
It allows us to use telescopes more flexibly to detect fainter galaxies, to do our science more quickly. In some cases, it allows us to explore options to reduce the impact of radio frequency interference, which afflicts a lot of radio astronomy these days. Of course, ASCAP and NWA have been moved to radio quiet sites, but our existing telescopes, radio telescopes at Parkes and Narrabri, are heavily influenced by local radio emissions, and there's many things we can do with this new technology now and in the future which might be able to allow us to better mitigate that local radio interference, which quite often just inundates and overwhelms the cosmic signals we're looking for. So it's a technology upgrade will allow us to do lots of new things in the future and perhaps mitigate our exposure to this local interference.
That's Professor Lister Stavili-Smith from the University of Western Australia node of the International Centre for Radio Astronomy Research. And this is SpaceTime. I'm Stuart Gary. Still to come, a key pre-launch test for the James Webb Space Telescope, and it was promising a spectacular celestial display over the next few months. But it now looks like Comet Atlas has shattered skywatchers' expectations as well as itself. All that and more still to come on SpaceTime. There's been an important milestone in the development of NASA's new James Webb Space Telescope, with a pre-launch test of its primary mirror being fully unfurled and deployed into the final configuration it'll have once it's in orbit next year. The test was carried out in a clean room at the Northrop Grumman facilities in Redondo Beach, California. Special gravity offsetting cables were attached to the mirror to simulate the zero-gravity environment its mechanisms will have to operate in once in orbit. Engineers and technicians carried out the full mirror deployment as part of a long list of tests now being undertaken prior to the telescope's final packaging for launch. The new orbiting observatory is slated to launch aboard a European Space Agency Ariane 5 rocket from the Kourou spaceport in French Guiana in March. The James Webb Space Telescope will ultimately replace the current Hubble Space Telescope, which, believe it or not, has now been in orbit for 30 years. It was launched in 1990. Unlike Hubble, which uses a 2.4-metre primary mirror and observes mostly invisible light, although it can venture into the near-ultraviolet and near-infrared occasionally, James Webb will use a much larger 6.5-metre gold-coated beryllium primary mirror, and it's designed to observe in lower frequency ranges, from long-wavelength visible light through to mid-infrared. This will allow the 6,500-kilogram observatory to study the very early distant universe, looking at high redshift objects whose light's been stretched into the infrared from their origin, often in the ultraviolet, by the physical expansion of space-time. This means the James Webb Space Telescope will be able to observe objects that are too old and too distant for Hubble to see. The telescope will be deployed into near-Earth space at the Lagrangian L2 position, a gravitational well located some 1.5 million kilometres away, directly on the opposite side of the Earth from the Sun. As well as allowing it to maintain its position with minimal fuel expenditure, this location will keep the spacecraft continually in Earth's shadow, helping it to keep cool the infrared technology it uses. This is SpaceTime. Still to come, Comet Atlas breaks apart, shattering not only itself, but also the hopes and dreams of skywatchers who were expecting a spectacular celestial display over the next few months. And later in the science report, discovery of 3 distinct variants of COVID-19. And growing concerns after people previously cleared for COVID-19 have been found positive after all, following a second round of testing. All that and more still to come on SpaceTime. Well, it seems Comet C 2019 Atlas, which had promised to put on a spectacular celestial display over the next few months, has instead shattered both skywatchers' expectations and itself by breaking apart into at least 3 or 4 major fragments. For a while there, the comet looked like it was going to put on one of the best sky shows in decades, with a stunning green glow in its coma and tail slowly turning blue as it approached next month's perihelion, its closest orbital position to the Sun. First discovered back on December 28th as a fairly innocuous little comet, Comet Atlas then began brightening rapidly in March, prompting many skywatchers to speculate it could eventually become as bright as Venus, and maybe even bright enough to be visible during the daylight. But a couple of days ago, astronomers began seeing chunks separating from the comet's nucleus, and that triggered the first alarm bells among skywatchers that something may be drastically wrong. And things have quickly deteriorated, becoming much worse, with the comet's nucleus now beginning to disintegrate into multiple fragments, forming what's called an elongated pseudonucleus, something usually seen during a major disruption of a comet. But then again, when you think about it, comets are famously erratic and hard to predict. Remember, they're frozen, muddy piles of rock and ice, and as they get closer to the Sun, the increased heat and radiation causes volatile materials to begin boiling away, which can inflict serious damage to the comet's structural integrity, turning once promising celestial sky shows into early oblivion. But then again, when you think of what's happening on planet Earth right now, that may not be such a bad thing. After all, historically, comets have always been seen as portents of doom, and now's probably not the best time for that. After all, right now there's a major locust plague in Africa. We've already experienced a burning bush here in Australia. Pestilence and disease are inflicting the entire planet thanks to COVID-19, so the signs are all there. Dare I ask if anyone's noticed 4 horsemen riding past? And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Scientists have found 3 distinct variants of COVID-19, which they've labelled A, B and C. Types A and C are found in significant proportions outside East Asia in Europeans and Americans, while Type B has become the most common type in East Asia. The findings, reported in the Proceedings of the National Academy of Sciences, claims Type A was the original human COVID-19 variant and the closest to that found in bats and pangolins. While it's still present in Wuhan, China, where it originated, it surprisingly wasn't the most common variant there. Mutated versions of Type A were found in Americans who had lived in Wuhan, as well as patients in both the United States and Australia. But Wuhan's major variant was Type B, which was directly derived from Type A and is separated by just 2 mutations. It's become the dominant variant across Southeast Asia, and that suggests some sort of resistance against this type outside East Asia. The third variant, Type C, is apparently the daughter of Type B, and has become the major European variant. Type C has been found in early patients from France, Italy, Sweden and England, as well as in Singapore, Hong Kong and South Korea. There are growing reports that people who had previously been cleared for COVID-19 after suffering from the disease have been found positive again following a second round of testing. The Korean Centers for Disease Control and Prevention says the virus may have reactivated itself rather than the patients becoming reinfected. Mind you, it admits there is a possibility that early COVID-19 tests were showing false positives. It does raise serious concerns because it had previously been assumed that people who've recovered from COVID-19 would be able to go out into the community and resume their lives without fear of infecting others. And just before we leave COVID-19 for now, a word of warning: if you have a cat, keep it indoors at all times, because scientists have found that humans can infect their kitty cat with COVID-19. Now, don't misunderstand that there is no evidence of cat-to-human transmission, but once a cat's infected, it can pass it on to other cats. The new advice has come after Nadia, a Malaysian tiger at the Bronx Zoo in New York, tested positive for COVID-19 and has passed it on to other tigers and lions at the zoo. The good news is Nadia and her companions have all made a full recovery. Scientists using data from the European Space Agency's Copernicus Sentinel-5P satellite have discovered an ozone hole opening up over the Arctic. The ozone layer is a natural protective layer of gas in the stratosphere that helps shield life on Earth from the sun's harmful ultraviolet radiation, which is associated with skin cancer and cataracts as well as other environmental issues. Small ozone holes have opened up above the Arctic before. This latest hole is thought to have been triggered by unusual atmospheric conditions, causing powerful stratospheric winds to trap freezing cold air in a polar vortex, which in turn caused ozone levels to plummet. The current hole is less than 1 million square kilometres in size. Now, that's quite small compared to the Antarctic ozone hole, which can reach 25 million square kilometres in size and remain open for 3 to 4 months on end. As well as strong winds and extremely cold temperatures below minus 80 degrees Celsius, ozone holes can also be formed by man-made chemicals such as chlorofluorocarbons or CFCs. These have now been banned by the Montreal Protocol. However, China continues to produce and use them in large industrial quantities. Scientists have published the first ever study to survey identity ownership separation problems in cats. The findings were reported in the journal PLOS ONE, based on results from 130 cat owners, researchers finding that 13.5% of pets displayed troubling behaviour in their owner's absence. This included destructive behaviour, aggression, anxiety, and depression. The researchers found that cats with separation issues tended to come from households with no female adults, or alternatively with more than one female adult in the household. Another problem was households with owners aged between 18 and 35, probably don't spend enough time with their pets. Single pet households were another problem, so believe it or not, no matter what you may have been told, cats do like company. And another problem was households with no cat toys, suggesting that cats also become bored. Although these findings are all limited by the owner's ability to accurately interpret their behaviours, it may help identify ways to improve the well-being of our feline friends. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favourite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.